Hello and welcome to lecture 13 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to derive an expression for the drift current. Okay, so imagine we have a tube and there are particles inside this tube and they are all traveling with the same velocity in the horizontal direction. So these arrows here represent the velocity. So in this example, we have a gas of particles and they all have the same velocity. So there is a preferential velocity in this example. And the type of current that arises from a gas of particles having a preferential velocity is called a drift current. So that's the definition of drift current. Now, usually, the velocity is caused by a force. For example, if the particles are electrons, then the relationship between the velocity and the force is given by Ohm's law, which states that the velocity is proportional to the electric field. But that's not what we're interested in this lecture. In this lecture, we're going to assume that there is a preferential velocity. So the velocity is a given, and we want to find a relationship between the velocity, the concentration of particles, and the current. So you can understand this lecture as being a lecture in logic. It's not in physics, because we're not dealing with the origin of the velocity. We are just dealing with the logical relationship between current, concentration, and velocity. And even though velocity is strictly speaking a vector, we're going to treat it as a scalar here because we're going to assume that the particles are propagating in the horizontal. But I don't want to call it a speed instead of velocity because I want to allow it to have negative numbers. Later on, we're going to allow it to go backwards. So I'm going to stick to the term velocity even though we're treating it as a scalar. And we're treating it as a scalar just to simplify the description. Okay, so current, the definition of current is the number of particles that crosses a given cross-sectional area, which I'm calling A here, per unit of time. So it's the same definition of flux, okay? Is the number of particles crossing some area per unit of time. Now, let's make a mental experiment, a thought experiment. Let's suppose that we set a timer, and then we draw an imaginary line here in this line of particles, and then we set our timer and wait until this last line of particles reach or cross the area A. And let's call this time delta t, and the number of particles that crossed the area in this interval of time delta t, we're going to call n delta t. So by definition, the current is the ratio of the number of particles to the interval of time that took for this number of particles to cross. Now we want to relate this number of particles with the concentration. So if in our thought experiment, this line of particles was the last one to cross the area in the interval of time delta t, that means that all particles inside the volume delimited by the distance these particles traveled to cross the area will have crossed the area in the interval of time delta t. So this number of particles is just the number of particles inside this volume. So it is the concentration of particles times the volume, and the volume is the area times this distance L. So we can use this expression for the number of particles that cross the area A in the interval of time delta t. Now, of course, this length is related to the velocity of the particles through the time it took the particle to reach the cross-sectional area A. If the velocity is v and it took delta t seconds for the particles to cross, that means that the distance the particle propagated is v times delta t. So we can use this expression here, and then we delta t cancel because it's the same time, the same interval of time, and we get this expression for the current. So this is the number of particles crossing the area A per unit of time. But usually we like to express the current in terms of the current density, which by definition is the current divided by the cross-sectional area. So when we divide this term by A, we end up with rho times V. So it's the concentration of particles times the velocity. So this is a logical relationship. There's no physics here. Given the definition of concentration, given the definition of velocity, and given the definition of current density, we reach this equality. Okay? So it's important to tell apart what is logic, math, from physics. There's no physics here. Physics come in when we describe this velocity in terms of the force that caused it. Now, we found this expression assuming that all particles had the same velocities, but we can generalize the expression assuming a gas with distribution of particles, but not of all of them with the same velocity. Let's still assume that they all have horizontal velocities, just to make the reasoning easier. But let's now allow the magnitude, the speed, to change, and also the direction. It could go to the left or to the right. Now, in this case, we can take a specific group of particles. So let's suppose that a group of particle n, all of these particles have velocity vn. So if we're assuming that there is a group of particles where all particles in this group have the same velocity, then we can use the expression we just derived to obtain the contribution to the current from this group. So this we're calling the group N. And because current is just number of particles crossing an area in an interval of time, these numbers add up. So to find the total current, we can just add up the contribution of each group. So here I am assuming that we have m groups of particles. So this becomes an expression for the total current density. And notice that V could be negative. So this number could be even 0 if, say, half of the particles are going to the right and the other half is going to the left with the same speed. Then we would have J here being, for example, 0. Now we want to express the total current in terms of the average velocity. So the average velocity is the sum of the velocities of all particles divided by the number of particles. So it's a simple average. So n here is the number of particles, and the term in the numerator is the sum of the velocities over all particles. We are expressing this sum taking the contributions of each group. So this term is the contribution of the group N. So if the particles in group N have velocity Vn, then when we add up all these velocities, we're going to get the velocity times the number of particles in the group N. So this term is the number of particles in the group N. And when we add the contributions over all groups, we get the sum over all particles. So this is just a simple average. Here I'm just repeating this expression because we want to change it to express it in terms of the concentration. So to do that, we multiply the numerator and denominator by the volume, and then we move this term here, this term here. So this term is the number of particles with velocity Vn divided by the volume. So it is the concentration of the group N. And this term is the total number of particles divided by the volume. So this term is the total concentration. So notice that the term in the numerator coincides with the total current. So this term is the total current density, and from this expression we infer that the current density is given by the concentration times the average velocity. So this is a more general expression. And this is why we say that the drift current is associated with a preferential velocity. So what do we mean by a preferential velocity? It just means that the average velocity is different than zero. So if we have a preferential velocity, we have an average velocity different than zero. So when this average is not zero, we have a drift current. And remembering, this is a logical expression. There's no physics here. Physics comes in when we relate this term, the average velocity, with the force. Okay? Okay, so that's it for today. We have an expression for the drift current, and our next job is to find an expression for the diffusion current. But to do that, we need to use the concept of solid angle. So I want to say a few words about the solid angle before we deal with the diffusion current. But this is not terribly important for our purpose. So if you want, you can skip the next lecture and take the result we're going to derive there for granted. But it's also not very complicated, so I encourage you to watch it. So I either see you in the next lecture or in the lecture on diffusion current.